We're going to finish up talking about higher order linear ODEs, so not linear, so linear, by looking at variation of parameters. Okay, so let's just take a few minutes and review variation of parameters that we did back in chapter 5. So I think it was section 5.7, if I remember right. Yeah, because we had 3 sections on undetermined coefficients. So section 5.7 is where we did this before. And here was the setup here. We had our y double prime plus p of x y prime plus q of x y equal to f of x. All right. So we had a linear differential equation, and it was equal to something that wasn't 0. So this was a non-homogeneous linear ODE. And so we proved in chapter 5 that the first thing we do is we go after the complementary solution. And to get the complementary solution, we set the linear differential equation equal to 0. And since it was a second order equation, we could expect 2 linearly independent solutions to this. So we would get a c1y1 plus a c2y2. And then we would go off to try to find a particular solution. So a particular solution would be a solution that addresses the homogeneous part. And depending upon what the diffie-q looked like and what the non-homogeneous piece looked like, sometimes we could do undetermined coefficients. So if we had a constant coefficient equation and the f of x was built up of exponentials, sines, cosines, and polynomials, we could do undetermined coefficients. And the end of last week, we reviewed how that extends to higher order derivatives or differential equations. And it extends exactly in the way that everybody would think it would. All right. But another technique we had, sort of instead of a guess and check, is we used variation of parameters. And variation of parameters is a lot like, is analogous to the quadratic formula in the following sense. When you're solving a quadratic equation, if it doesn't factor nicely or you can't extract roots, we could always run things through the quadratic formula and it would spit out the solution. It might not be the most efficient method, but it always works. That's how variation of parameters is. Once you get your complementary solution, then you assume your particular solution looks like, well, we vary the parameters. So C1 and C2 being constants, that's a 2-parameter family of solutions. We would vary the parameters, say call it U1 and U2, and we would make a simplifying assumption that when we took the derivative here, the U1 and the U2, we're not saying they're constants, but when you take the derivatives here, we made a simplifying assumption that the derivative would look like what you'd get if U1 and U2 were constant. So this was a simplifying assumption we made. And basically that means that we're assuming the other half of the product rule is 0. So once again, this is all review of 5.7 here. So that meant like U1 prime y1 plus U2 prime y2. We assumed that was 0. So this was our simplifying assumption. And then when you stuffed this into the differential equation using this simplifying assumption and set it equal to f of x, we got another equation. We got u1 prime y1 prime plus u2 prime. Oops, I'm sorry. I had that was fine. I just had it sort of in a weird place. Y2 prime equal to f of x. This was a result of plugging it into the differential equation. And remember, we had to be very careful when assigning this f of x, because we had to make sure that the f of x here, we had to make sure that we had a leading coefficient of 1 here. All right, so we'll review that in the particular problem we do today. All right. And so then at this point, we would hit this with everyone's favorite yet highly inefficient method to solve systems of equations, Cramer's rule. So Cramer's rule allowed us to solve for, well, u1 prime and u2 prime. So if we think of these as the unknowns, we would create three different matrices. We would have the determinant of the coefficient matrix D. So look at the coefficients of the unknowns. That's y1, y2, y1 prime, y2 prime. And this matrix had a special name. Does anyone remember the name of this matrix? Well, it's the determinant, but what's the name of it? Yeah, the Wronskian. So this was the Wronskian. And we proved that if y1 and y2 are linearly independent solutions to a differential equation, then the Wronskian is either always 0 or it's never 0. And we would need it to be not 0 in order to use Cramer's rule. All right, so that was our determinant D. And then we had two other determinants, a D1 and a D2. So Cramer's rule says to get your D1, what you do is you replace the first column with the right-hand side of the equation. So we're going to replace y1 and y1 prime with 0 f of x. And we'll keep the second column the same. And this one isn't too bad. This one actually works out. We can do the zig minus zag kind of a thing. And we would get a minus y2 f of x. And then for D2, we would replace the second column with the right-hand side. This would give us y1, y1 prime, 0 f of x, and go through the zig minus zag. That gives us a y1 f of x. And so then, via Cramer's rule, u1 prime was minus y2 f of x over the Wronskian. u2 prime was y1 f of x over the Wronskian. And then we would integrate these to get u1, u2, and then finally we put all the pieces back together and get y is u1, y1 plus u2, y2. And the coefficients that would pop out here, like if you, or the arbitrary constants of integration c1 and c2, this would actually capture everything, the yc and the yp then. Okay. So that was, that's a bird's eye overview here of the variation of parameters. Once again, that was from section 5.7. Okay. So for variation of parameters, the first thing we had to do was put the diffie-q into the correct form to get the correct f of x. And then we had to find the yc. And then we had to calculate a couple of determinants. Well, really the Wronskian. That's really the only one we needed. And then we would get u1 prime, u2 prime, and then you'd be good to go. You just put all that together. Okay. So how does this generalize to higher order differential equations? Well, as fate would have it, Cramer's rule generalizes. And since Cramer's rule generalizes, we can generalize everything we've done here. All right. So if you had Calc 3, we talked about 3 by 3 determinants in Calc 3. Does anyone remember where we used 3 by 3 determinants in Calc 3? What did we use those to help us calculate? Do you remember? Yeah, the cross product. So as the cross product was in there. Let's just remind ourselves how 3 by 3 matrices break down. If you're given a 3 by 3 matrix and you're trying to find the determinant of it, you can assign signs, plus and minus signs, across the top here, plus, minus, plus. And you take plus A times, and then you would wipe out the row and column that the A is in, and take the determinant of this smaller 2 by 2 matrix. And then we would have plus, minus, plus. We'd have a minus then. B, wipe out the row and column the B is in, and take the determinant of that little 2 by 2 matrix. And then once again, plus, minus, plus, plus C times the determinant of the little matrix you get by wiping out the row and column the C is in. Right? So this is called expansion by minors. So going through this, and if you had me in Calc 3, this is the exact same example we use. So let's get this one set up, plus, minus, plus. We're going to have 3 times. You wipe out the row and column the 3 is in. You got a negative 1, 5, 1, 4. Minus 1 times, wipe out the row and column 1 is in. You get a 0, 5, 2, 4. And then we're back to plus 2 times, wipe out the row and column it's in, 0, negative 1, 2, 1. And now for the smaller determinants, you do the zig minus zeg like we did before. So minus 1 times 4, minus 5 times 1, 0 times 4, minus 5 times 2, 0 times 1, minus negative 1 times 2. And then you go through the arithmetic here. 3 times, you got a minus 1, minus 4, minus 5. Minus a 1 times, a minus 10, plus a 2 times, a positive 2. So you get a negative 27, plus 10, plus 4. There's your negative 13. Is the 3 by 3 matrices coming back to you? How to do those determinants? So what's Cramer's rule look like for 3 by 3? So in your standard Cramer's rule setup here, you've got 3 variables you're looking for. So your unknowns are x, y, and z here. And you have 3 linear equations. So linear equations, remember, means that x, y, and z are all to the first power. We're notating the coefficients here with subscripts. So if you're in linear algebra, this is sort of old hat to you. The first number in the subscript tells you which equation you're in. So A1 means the first equation. So A11, that's your coefficient of the first variable x in the first equation. A12 means you're the coefficient of the second variable y in the first equation. A13, you're the third variable, you're the coefficient of the third variable z in the first equation, all the way down the line. So the first subscript here is just telling you what equation you're in, and the second subscript is telling you what variable you're attached to. Okay. So Cramer's rule says if the determinant of the coefficient matrix is not 0, you're going to get a unique solution. So not only is there a solution, but there's only one. Once again, the determinant, how do you get this determinant set up? It's the determinant of the coefficients. So the first column is the coefficients of A. The second column is the coefficients of Y. And the third column is the coefficients of Z. So it's the generalization of what we did back in the 2 by 2 case in section 5.7. And now we're going to have 3 determinants go along with our determinant D. So this determines, pun intended, if you have a unique solution. If that's not 0, then we've got these three determinants, D1, D2, and D3. How do we get those? The same way we got D1 and D2 back in the 2 by 2 case. What we do is we go in. For D1, we replace the X with the constants on the right-hand side. So instead of the X, we have the constants. We keep the Y and the Z column the same, and that number is D1. For D2, we keep the X and the Z the same. We replace the column of the coefficients of Y with the constants. And then for D3, we keep the columns for the X and the Y the same. And we switch out the column of Z with the constants. Right? So it's literally the same exact process we had in 2 by 2, except now we've got this, we're tacking on this Z, we're tacking on this third variable. And then we get the same formulas as before. So you can see why we need D not to be 0, because we're dividing by D. Right? All right, so let's actually go through and work this example, make sure we're all up to date on these 3 by 3 determinants. So let's first off, we have 3 equations. They're linear equations. All the variables here are to the first power. It's already written in sort of the standard form. So we'd start off by calculating our determinant D. This is the determinant of the coefficient matrix. So the first column will be the coefficients of X, Y, and Z. So what would be the first column here? I'm just writing down the coefficients of X, so what would that look like? Yeah, so the coefficients of X, yeah, so as you go down, it would be 1, 2, negative 3. And then for the Y's, it's 1, negative 1, 5. And then for Z, it's 1, 1, 7. All right, and there you go. So Zoran put them as rows there in the chat. You can see that. Okay, so let's go through and multiply this out. Once again, we're going to assign our signs here, our plus, minus, plus, alternating signs. So we're going to take all the coefficients here are going to be 1. You wipe out the row and column that the X is in. You get the little 2 by 2 matrix, negative 1, 1, 5, 7. Minus 1 times. Wipe out the row and column the Y is in. 2, 1, negative 3, 7. Plus 1, wipe out the row and column the Z is in. You get a 2, negative 1, negative 3, 5. So take a minute and make sure we all good on the expansion here into these little 2 by 2 determinants. So now we evaluate these as usual. So I've got the 1 here. You do the zig minus the zag. I've got a negative 7 minus 5. Minus a 1 times, you've got a 14. Minus a negative 3. So that's really 14 plus 3. Plus 1 times 10 minus a positive 3. So you got your negative 12 minus 17 plus 7. So what a minus 22 looks like? What's all said and done? Any questions on calculating these 3 by 3 determinants? So let's just go in and set up the D1, D2, and D3. And I'll let you go through the actual calculations of that. So for D1, we're going to replace the x's with the constants. So the constants are going to go in here, and then we'll keep the y and the z the same. So the constants here are the 3, 0, 7. The y's would be 1, negative 1, 5. And the z's would be 1, 1, 7. And then once you calculate this, the x would be d1 over d. So if our d is actually correct, being negative 22, then the d1 should be a negative 22 as well to get x equals 1. To get y, we would do d2. So to get to d2, you'd keep the x and the z the same, but you'd switch out the constants. Whoops. For y. So you keep the coefficients in for x, 1, 2, negative 3. Plug the constants in for y, 3, 0, 7. And then z, 1, 1, 7. And then to get y, you take your d2 over d. And once again, provided our d is correct, d2 should work out to be a negative 44 to get y equal 2. And now we've got a z in there. So how do we get the d3? The same way we got the d1 and the d2 for the x and the y. We're going to take, instead of having the coefficients of z in there, d3, you're going to have the coefficients for x and y, but we're going to switch out the coefficients of z for the constant. So x is 1, 2, negative 3. 1, negative 1, 5, and then we switch this out, 3, 0, 7. Z then would be d3 over d. And what would z have to be for this to be correct? If this is correct, then what should the d3 work out to be? Well, it should work out to be 0 if we've done all the calculations correct. It should work out to be 0 for z to be 0 there. So we should have 0 over d, which is 0. Oh, yeah, there you go, yeah. So, once again, as you go through, the first thing you should do before you jump into the homework, do a couple of these 3 by 3s. Make sure you're getting the stuff to tie out. This is a good example to kind of go back and debug your solutions, because this is, of course, I rigged these to be friendly numbers, so I think they'll work out for you. Okay, so that's how Cramer's rule works in 3 by 3. And so when it comes to variation of parameters, we're going to stick to third order here, because once you see how it generalizes to third order, you'll see how it generalizes to all the orders. Okay, so we've got, basically, if we go back to what we talked about, reviewing section 5.7 here. Where was it? All right. So we needed to get the leading coefficient of the highest order derivative to be 1. That's how we identified our f of x. We found our complementary solution. Since we were second order, we had 2 linearly independent parts, and then we made assumptions about the particular solution, being these multiples, function multiples of those linearly independent parts. Same thing's going to happen here, third order. The very first thing you got to remember is you want the coefficient of the highest order, in this case, third order. So the coefficient of y triple prime has to be a 1 in order to correctly identify the f of x. Now, as I recall, I was very happy. I think pretty much every single person remembered to do this back when we had this show up in section 5.7, and then also in with the Cauchy-Eulers we had then after the break in chapter 7. Okay. So we're going to assume P, Q, and R and F are all continuous in some open interval containing any initial condition we would have. The first thing we do is we find the complementary solution. All right, find the complementary solution. Since we're a third order linear equation, we're looking for 3 linearly independent parts. How do we get those linearly independent parts? Either undetermined, or either the e to the mx or the Cauchy-Euler, which we'll review here in a minute. Now, when you go in to do your Cramer's rule, this Vronsky is going to be your determinant D. And just like with second order linear equations, if you have linearly independent parts, y1, y2, and y3, and they're all solutions of a linear differential equation, the determinant Vronsky is either going to be always 0 or never 0. So this should never be 0 if you've got 3 linearly independent solutions in there. And now we're going to call W12, W13, W23. Notice these are the Vronskians. These are the Vronskians for two of the functions at a time. Okay. So where do these come from? Well, they come from the writing out the equations here. So when we had our D1 and D2, for the system of that we got from the differential equations, this minus y2 and y1, these came from the determinants of this matrix. These are the D1s and D2s. So if you do the 3 by 3 equivalent to that, you're going to have these, when you do that expansion, you're going to have zeros, and these little 2 by 2 matrices will pop out. Okay? And that might be a fun exercise, especially if you're in linear algebra and you're hip to how determinants work. Set up the system that you get, and then show that these little Vronskians fall out. I mean, that would be a nice little project, actually. If you're hard up for a project, you want a fun little project to do. If you're in linear algebra, especially, you can explain where these formulas come from. But it's just one dimension up of what we did in 5.7. And so you would stuff these in, hit this with Cramer's rule. So here's your f of x W23 for u1. So notice u1 prime is f of x times the Vronskian of the other two functions. u2 prime is minus the Vronskian of the functions 1 and 3. And then u2 involves the Vronskian, u3 prime is going to involve the Vronskian of 1 and 2. All right. So once again, what we're going to do here for the last bit of this is we're going to get all these things set up, and then it'll be, you can go in there and go through all the details to see that all tracks out. But hopefully you can see that this is just one dimension up. And you can see that if I had a fourth order equation, we could just make this a 4 by 4 matrix, and these would each be 3 by 3 matrices. You follow? The nice thing about linear things out in the wild is if you have a linear system, linear things tend to extend to higher dimensions in a very natural progression. Okay. So let's take a look at this example. There's a hint here that says this is a Cauchy-Euler equation. So we got to remember, how do we spot Cauchy-Eulers? Because there's one like this on your last take-home coming up. How do we know this is a Cauchy-Euler? And then follow-up question, what do we do with Cauchy-Eulers? So what about this diffie q? Yeah, the power of x matches the order of the derivative. Okay, so we go after the complementary function first. That's a 4x cubed y triple prime plus a 4x squared y double prime minus a 5x y prime plus a 2y. And since we're going after the complementary solution, we set all this equal to 0. Now, do you remember what assumption we make here? For Cauchy-Euler, it's a little different than for constant coefficient. For constant coefficient, we assumed y equals e to the mx, but for Cauchy-Euler, we assumed that y equals x to the what? Because if we think of what's going on here, anytime you take a derivative, we're slapping on a power of x. So we take a derivative, one derivative, we multiply by x, two derivatives, we multiply by x squared, three derivatives, x cubed. So every time we would take a derivative and lose a power of x, multiplying by x puts it back together again. All right, so then we look y equal x to the m. So y prime would be mx to the m minus 1. Y double prime, which is as far as we took it back in chapter 7. Oops. And so the quote-unquote new thing would be y triple prime. So then you would stuff each of these into the differential equation, and once again, you'd have an x to the m term here. When you plug this in for the y prime, you'd have x times x to the m minus 1. That would give you an x to the m term here. Here you have an x to the m minus 2 multiplied by x squared gets you back to x to the m. And here's your x to the m minus 3 multiplied by x cubed gives you x to the m back. So just like in chapter 7 when we did the Cauchy-Euler, we can factor out that x to the m power, and that's going to give us a polynomial equation. So it's going to be 4 times m times m minus 1 times m minus 2 plus 4 times m times m minus 1 minus 5 times m plus 2. And that becomes our equation to help us figure out what the m's are. And so at this point, you can go off to Desmos, do your synthetic division, all that good stuff. Just as a reminder, if depending on how much you have, you could always go off to Desmos and help you find these roots. I can just plug in the function we got there. I didn't have Desmos ready. We could stuff in the function there on the left. Come on, Desmos. Right, so we could do f of x equals 4x, x minus 1 times x minus 2 plus 4x, x minus 1 plus, or minus 5x plus 2. And there we go. And, thinking back to algebra and Diffie-Q, we've got a third order equation here. So we're looking for 3 linearly independent. In this particular case, we're looking for 3. We got 3 x-intercepts here, negative 0.5, 0.5, and 2. So Desmos is telling us that the solutions to this, negative 1/2, positive 1/2, positive 2, you would verify this using your synthetic division or whatever. Right. Now what's nice about these numbers for us is that they're all different. So they all correspond to different powers of x. And different powers of x we know are linearly independent. So there's that. So remember, these m's go on. There's your powers of x's. So we can identify y1 is x to the minus 1/2. We could pick y2 equals x to the 1/2. And the third linearly independent solution is x squared. Does it matter whom you assign what? No. As long as you're consistent, everything will come out in the wash. But you need to let me know what's your y1, y2, and y3 before you set everything up. Right. Any questions on finding those roots and then what to do with those roots once you find them? Now, this didn't happen here, but just a little recall here. What if we had gotten 2 of the same? Yeah, what if we had gotten minus 1/2, minus 1/2, 2? Do you remember how do we eliminate duplication with Cauchy-Euler? What would we multiply by to get a linearly independent function that's close enough for the differential equation, but not too close so as to be snatched up into the c1x to the minus 1/2? Do you remember what factor we tack on there? Not an x. Not x. If this were constant coefficient, yep, we would do the x. But if we put an x on there, that would actually change the power of x, which would require us to have a different root. It was actually, we would tack on natural log x. So we tack on natural log x. Okay. I think Cauchy-Euler we did back in the day. I believe it's section 7.2. It was in chapter 7 at some point. If we had, so if we had, say, all of them were that, you eliminate duplication by tacking on factors of natural log x. And you could either get that by doing like a reduction of order or by doing that substitution. This is going back a fair amount though. Whoops, not squared, but just to the first power and then squared. So in Cauchy-Euler, tacking on an x, like undetermined coefficients, is like tacking on a factor of natural logs. That's just a little FYI for you as you perhaps work through some of these other problems. Okay. So now what we would do is set up all this stuff. So we found the YC. And once again, we're going to just label who we think the y1, y2, and y3 are. So we'll call y1 x to the minus half, y2 x to the half, y3 x squared. And now we're running through variation of parameters. So we would have the Wronskian. We would take the three functions and then take derivatives. And then we would take the second derivatives here because we'd fill out the 3 by 3 matrix. And we get whatever that is. And since this is a Cauchy-Euler, we're going to be choosing a positive or negative interval to be on. So it'll be non-zero on whichever interval we pick. So we'd have to get that. This would be some function of x. And then we go through and look at the Wronskian, the little Wronskians, Wronskian of 1 and 2. So you just do the Wronskians of 1 and 2. The Wronskian of 1 and 3. And the Wronskian of 2 and 3. Okay. Once again, all these are coming from Cramer's rule. Right. And then you would piece those together to get your u1 prime, u2 prime, u3 prime. Now remember, when you go to use these formulas, whoops, where are they? When you go to use these formulas, for then u1 prime, u2 prime, u3 prime, the f of x we're using up here comes from the version of the differential equation where the leading coefficient there is a 1. So if we look at the equation that we've got here to work with, so this is the non-homogeneous equation we've got to work with here. See, the cat's warning you. Don't forget this step. It'll throw everything off. In order to figure out the correct f of x, I'm going to have to divide both sides of this equation by what? Yep, 4x cubed. So you divide both sides by the 4x cubed. And so the f of x you want for the variation of parameters would be 30x squared over 4x cubed. You can go reduce that down. What's that be? 15 halves x to the minus 1. That would be the f of x you would then plug into the formulas. Okay. So the big takeaway today, right, we spent a good 10 minutes reviewing how the variation of parameters, where that came from. It came from Cramer's rule back in section 5.7. Variation of parameters here in section 9.4 comes from Cramer's rule. Everything we did comes back to Cramer's rule and extending that from a 2 by 2 system of equations to a 3 by 3 system of equations. Okay. And once again, at this point in the semester, I don't know if there's any value going through all these different things. But when you go through and get your u1, u2, and u3, you should be able to simplify your answer enough to just get really one term for the particular piece, the 2x squared natural log x. So as you go through, and this is very typical in variation of parameters in chapter 5, oftentimes you would get other parts as you would go through your integrals and simplify things. You get other terms that could be combined up with the arbitrary constant pieces, C1, C2, C3. So when you go through this, keep an eye out for that. Like if in one of your answers you end up getting, you might get like a 5/7 or something, x to the minus 1/2. That's going to be able to get combined into a C1, x to the minus 1/2. So you want to keep on the lookout for that and see if you can simplify your answer. And then, of course, we've got some extra practice for you in the homework. And that's all. That's it. That's Diffie-Q. What I might do, I might post a solution. I might post a video to watch if you're interested on Airy's equation. Airy's equation was a Diffie-Q you looked at early on in the semester. It's a type of equation you'd solve using power series. That might interest you. That might be a nice project. I think I posted it earlier as well. But just to remind you here, there is no test 15. There's take home 15 and then a project. If you elect to do it, the projects we present them a week from tomorrow. That's one of the final exam days. The system gave us 2 for some reason. I'm not sure why, but we'll just do that. Let's take a look at this last. Let's look at take home 15. It'll become available on Wednesday, but there's 2 problems. Okay, so this will be due Wednesday, May 8th. You got initial value problem. It's a constant coefficient. So you could hit this with your undetermined coefficients. So this is like 9.2 and 9.3. So method of undetermined coefficients will handle that one. I think someone asked, can you Laplace transform these? Yeah, you can. You can Laplace this if you want. Just you'll get that third degree polynomial showing up in the denominator, which you would have to then factor to do partial fractions on. So you can do these with Laplace if you so choose to. Then number 2, here's a variation of parameters. It's like the one that's on the handout. We kind of got it set up today. Is it really a third degree equation? Well, no. It looks like it is, but it's actually a second degree equation in disguise. But you can treat it like a third degree equation, go through all the good stuff, variation of parameters. There is no y term here. That's just going to make the equation easier to work with, to get your roots from. Once again, if you're gonna use that variation of parameters, you need to make sure that you rewrite it like this to get the correct f of x before you go off and use your formulas. This is an initial value problem, so in addition to getting your yp, once you get the yp, you got to stuff everything in to determine your constants on your complementary solution. So those couple initial value problems. And once again, you can check these on Desmos. You can check that your solution works. You can check that the initial values work. So you can have every confidence in the world when you turn it in next week that you're good to go. Okay. And that's the course. So I'm just going to be hanging out here the next few days. If you have questions, feel free to tune in during class time and chat about your things. If you're interested, if you've got some project ideas, you're not quite sure what you want to do, feel free. We can talk about those as well. So the project presentations will be next Tuesday. I'll be putting out my office hour schedule here at the end of the week once I figure out the best time for the Calc 1 students. I'll have some online office hours in the morning, and then I'll have some afternoon office hours for the Calc 1 students in the evening. Okay? Thanks for tuning in. Enjoy the day, and maybe we'll see you tomorrow. If not, we'll see you on Tuesday.